Okay, I think today's the microphone has some problem with the. Anyway, so I will ask the engineer to adjust the volume. Okay, so we have developed several properties of determinant functions based on the three axioms to be fulfilled by any determinant function. So we'll continue on some more properties of determinant function. Okay. The set of rows of an n-dimensional matrix A is linearly dependent if and only if that the determinant of A is 0. So this is one way to know that to justify whether the determinant value of specific n-dimensional matrix A to be 0. Okay, right? And this is quite a nice property because that's if the value of the determinant is 0, then we know the rows of the matrix A form a linearly dependent state. Okay, so we first prove the forward part. Now, so we assume the set of rows of matrix A is linearly dependent. So since the state one of rows is linearly dependent, right? So there are scalars alpha 1 up to alpha n, not all 0, such that a non-trivial linear relation exists. So alpha 1 plus alpha 2 are 2 plus alpha n equals 0. Okay? Right. So you see, because the coefficients of i's are not all zeros, so this linear relation is non-trivial. Okay? It's non-trivial. So assume that alpha I not equal to 0, right? So because one of them is non-zero, so we just assume, just take our alpha I. Then we have, so we can oh. Let's see. So we can divide. We can divide the linear relation by alpha I. So this, in this way, we can turn the coefficient of alpha I to be 1. So alpha I, so the coefficient is 1. Okay, so now I find a typo. There. So I forget to divide the last coefficient alpha m by alpha I. Okay, so please correct it in my lecture notes. Okay. So by applying n minus 1 replacement row operations, E, so that so we will add, this is the ith row of the matrix A, right? So we want to turn the ith row of matrix A to 0, all right, to 0. How? Well, we can add a multiple of alpha 1, right? The first row, a multiple of alpha 1 to the ith row. We add a multiple, etc., the multiple of alpha, the I minus 1 row to the ith row, right? By using the replacement row operation. Okay, add them. So this is alpha for all and j not equal to I. On A. Right? So the resulting matrix okay, so the B becomes 2, 1. Okay. Okay, so that is, so we apply okay. So when applying this elementary matrix, we will multiply the first row by alpha 1 divided by alpha I, and then add to the alpha I. So that is this term, etc. And by applying this elementary matrix, we multiply the I minus 1th row with this scalar and add to the ith row. So it's this term, etc. Right? So we can do it. So B is obtained by doing n minus 1 replacement row operations on the matrix A. All right, and this linear combination becomes to the 0 vector here. So this whole thing becomes to the 0. All right, so the determinant of B is equal to, so 0 is equal to the determinant of B. All right, so this is by the 0 properties. So that is theorem 4.1.b. So we know this is 0. And when applying replacement row operations, we will not change the determinant value. Okay, so this is equal to determinant of A. And so this is by axiom 2, right? Because they are all replacement row operations. Okay, and so we have done the forward part. Question? Big work part. All right, so we will use the, here we want to show Q implies P, right? And that means implies negative Q. So they are equivalent. So we are using the contrapositive argument here. So we suppose that the state R1 of rows of A is linearly independent. Okay? It's linearly independent, and so we will show that the determinant of A is non-zero. Okay, this is what we want to show. Now, by the invertible matrix theorem, right? A is row equivalent to the identity matrix. Well, I think there are a lot of, because the invertible matrix theorem has 16 statements, right? They are equivalent to each other. So a quick argument here is that if the matrix A has independent rows, linearly independent rows, then that there is no zero rows. Okay, in any row echelon form of A. Okay. And the identity matrix. So actually, so they are so there are lots of there are many ways to reach to this one. Okay. And by elementary row operations, A can be reduced to identity. Okay, so A can be reduced. All right, so you can say that we can apply that okay, so by row operations, so they are all elementary matrices, right? Either corresponding to replacement okay. So these are elementary matrices of type either corresponding row replacement row operations, scaling row operations with non-zero scalar, or swap of the ith and jth row. Okay, so this is, so we know that. All right, and okay, also applying replacement do not change. So do not change the determinant value. And applying scaling and the scaling operations, we are multiplying the determinant value by a non-zero scalar, and applying swap row operations will change the sign right? So we change the sign of the determinant value only. Okay, so we have determinant of identity is equal to alpha times the determinant of A, with alpha not equal to 0. Right? So if E1 is the replacement operation, then after doing on the A will not change the determinant value. Right? But if some EI is a scaling corresponding to a scaling row operations, then it will multiply the determinant value by a non-zero constant. But if E sub I is a swap row operation, then we will change the sign only. Okay. So anyway, you will see that, right? That you have so that this is xm 2, xm 3, and for swap and the theorem 4.1 point, I think, 0.1. Okay. So by applying this xm1, xm3, and the theorem 4.1.1, that the determinants of this matrix is equal to a non-zero constant alpha times the determinant of A. Okay. But as we know, the determinant of the identity is equal to 1 by xm1. By xm1. So this implies that determinant of A is not equal to 0. Okay, so a contradiction to the determinant of A is equal to 0. Because in the theorem, here, the determinant A is 0, and we want to show that this is the set of row vectors of A is linearly dependent. But when we suppose that this set of rows is linearly independent, we find that we have a contradiction. All right, so what? Is linearly dependent. Okay, so we have done. Question? All right, so another version of theorem 4.1.4 is here. a square matrix is invertible. Okay, also called non-singular. If and only if its determinant is non-zero for any determinant function. Because up to now, we haven't proved the existence and the uniqueness of determinant function. But if there is one determinant function on n by n matrices, then for any square matrix, its determinant value must be non-zero. This is generally true. Okay, this is generally true. Okay, so this can be seen from the invertible matrix theorem and the previous theorem 4.1.4. Because the counterpositive of this statement is that the set of rows of a square matrix is linearly independent if and only if its determinant is non-zero. Okay, not this, not equivalent to not this one, right? Because P this is the logic. So negative P is just said that the set of rows is linearly independent. Negative Q says that the determinant of A is non-zero. Okay. Okay, we need a we need to mention the following theorem before we can give you an important property of determinant function. So that is so that x all right, suppose that in the n-dimensional Euclidean space, either over the real number or over complex number, that we just pick up a subset, okay? Pick up subset, which is linearly independent, okay? And the number of the size of the subset is from 1 to n. Okay. So suppose we just pick up such a linearly independent subset of column vector. Right? Then k equal to n if and only if the span of S is equal to Rn. All right, so this theorem gives necessary and sufficient condition to say that such a linearly independent set span the whole n-dimensional Euclidean space if and only if that the number of the size of this set is equal to the dimension of this Euclidean space. So this is only equal. So that means that if k is less than n, then this linearly independent set is impossible to span the whole Euclidean space. Okay, so we consider A1. So we let A to be a matrix formed whose columns are vectors in this set. So the dimension of this matrix is n times k. So it has k columns. Okay? Right. Now, since the columns of A form a linearly independent set, okay, each column of A has a pivot position. Right. By theorem 1.3.13 in chapter 1. We know that very well. So if a matrix has independent columns, okay, in given columns, then we know that the kernel of A should be trivial, right? So the kernel consists only 0 vectors. So that means that every column should have a pivot position. Why? Because if there is a column has no pivot, then the corresponding unknown variable can be set to be free. When we have a free variable, then the kernel of A is non-trivial. Okay, it contains infinite many solutions. Okay, so that each column A must have a pivot. As I said at the beginning of the semester, everything in this course will go back to chapter 1. Okay, go back to chapter 1. Elementary law operations, pivots, reduced to echelon form, such a kind of things. Okay, they are all elementary. So you have to be familiar with all the materials you learned in chapter 1. All right. All right. So that every column has a pivot. Now this implies. So how many pivots do we have? Every column has a pivot. So we have only k pivot. If we have only k pivot, but we have n rows, so the only first k rows has a pivot, right, in its row echelon form. So this implies that. So this implies that only the first k rows, right? We have n rows, right? But the only first k rows of A have a pivot position. Right? So it has a pivot position. Okay, so that's k equal to n if and only if each row has a pivot position, if and only if the linear system is consistent. Okay? So if every row of A has pivot position, then its reduced row echelon form has a pivot in every row. So there is no zero rows. Okay? There is no zero rows in the reduced row echelon form of A. So AX equal to B is consistent for all B in Rn over Cn by theorem 1.2.4. Okay, and this is if and only if the span of S, this is the column space of A, is equal to Rn over Cn by theorem 1.2.3. Okay. So all the needed information is in chapter 1, right? We need the theorem 1.3.13. We need the 1.2.4, 1.2.3, all in chapter 1. Okay? The cat disappeared. Great. I have 10 more minutes before a break. Right? So now we will show linearity of the determinant function on the first row. So for any n-dimensional vectors R1, for any n-dimensional row vectors R1, R1 prime, R2, Rn, and scalars alpha beta. We have the determinant alpha R1 plus beta R1 prime. All right, so the first row of the matrix is a linear combination of two row vectors, R1 and R1 prime. Right, now the determinant of this matrix is a linear combination of the determinant of two matrices. R1 here plus beta determinant R1 prime R2. So the determinant function is linear on the first row. Okay? Proof. If the index set from of the second to the last row vectors, right, from 2. If the index set of row vectors is linearly dependent, okay? So if the index set of n-1 vectors is linearly dependent, then the three index set, all right? The three index sets here. The first one is alpha R1 plus beta R1 prime R2 up to Rn. Because the R2 up to Rn is already linearly dependent, when you add one more vector into a linearly dependent set, this new set is also linearly dependent. Right? I think you have done some exercise before. Okay, and also R1. R1 prime. So the three index set corresponding to these three matrices, right? This one, this 3. So the three index sets are all linearly dependent. Okay? So they are all linearly dependent. But we just prove (4.1.c) Oh. Okay. 4.1.4. I'm sorry. So it's incorrect. So please correct it. Okay. So by 4.1.4, this is determinant 0. This is 0. This is 0. So the determinant alpha R1 plus beta R1 plus R2 Rn, which is 0. And 0 is equal to alpha times 0 plus beta times 0. So it's alpha determinant R1, R2, Rn, beta determinant R1 prime, R2, Rn. Okay, so we established the identity here. Okay, when R1, when R2 up to Rn form a linearly dependent state. All right, so the other cases assume the index set R2 up to Rn is linearly independent. Okay. Now, so this we call this S. All right. Maybe it's too. We can't see it. So we let. So this says let's be. Okay. All right. Now, since the size of the linear independent set is n minus 1, which is less than n, so the span of X is not equal to Rn, okay, over Cn, okay, by theorem. Oh, okay. I think the number A, B, C, okay, yeah, C, D. So by theorem 4.1.d, here, okay. By the theorem here, that because the size is not equal to n, so the span is not equal to Rn. And so we can pick up so by theorem 2.4.11, there exists a row vector R in Rn and are not in the span of X, such that the set union R, so we can increase the size of the linearly independent set, right? Remember that when we have so this is Rn, but we have a set, so this is 0 vector, we have R2, R3 up to, so we have R2 here, R3 here, Rn here, and its span here. Okay. And this spanning set is not equal to Rn, so we can find another vector R outside of the span of X, right? So that the new set is still linearly independent. Okay, that is the theorem 2.4.11, right? The last section, chapter 2. This is true for all vector spaces. Because in section 2.4, we consider general vector space. Okay, so we have that. Okay, all right, so we can pick up now. Such that this one is linearly independent. Okay, so this is linearly independent. Now again, by the previous theorem, 4.1.d, the span of this new set is equal to Rn or Cn. Why? Since the size of this new set is equal to n, right? Because X has size n minus 1. When you add one more vector into it, the size becomes to n. And when the size is n, then the span of this set is Rn. Okay, so the span. All right. Okay, so now we have the R1 here. Now R1 is just a row vector in Rn or Cn, right? Inside it, so that R1 can be spanned by the n vectors. So we have C1R plus C2R2 plus da 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 plus Cn Rn. This is R1. Okay, R1. How about R1 prime? Also, we can find D1R plus D2R2 plus da 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 plus Dn Rn. Okay. So R1 prime can be written okay, by as a linear combination of the vectors in this set, because that the span of this set is Rn or Cn. Okay, so any row vector can be written down as a linear combination of R, R2 up to Rn here. So here is that. Okay, so for some scalars, C1, C2 up to Cn, and D1, D2 up to Dn, and then the linear combination of R1 and R1 prime, the linear combination, right, becomes to alpha C1 plus beta D1 of R plus alpha C2 plus beta D2 R2 plus da 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 plus alpha Cn plus beta Dn of Rn. So this linear combination of R1 and R prime can be represented as linear combination of R, R2 up to Rn. Okay, any questions up here? All right, so now we have a very good position to do replacement operation. Okay, so here, alpha plus beta R2 up to Rn. Okay, so this matrix. Now, the linear combination now becomes to alpha C1 plus beta D1 R plus alpha C2 plus beta D2 R2 plus alpha Cn plus beta Dn Rn and R2 Rm. Now we can eliminate all the terms here. How? Replacement operation, right? So we can multiply minus alpha C2 plus beta C2 and add to here to cancel this term, right? By row operation, by any replacement operation. Similarly, etc. up to here, we can multiply alpha Cn plus beta Dn and then go to there. Okay, so that will turn to what? Alpha C1 plus beta D1 R R2 up to Rn. Okay. By how many replacement of operations? By n minus 1 replacement row operations. Okay? So we can reduce this matrix to this matrix by n minus 1 replacement row operations. So what is this implication? So that means that the determinant of this matrix alpha R1 plus beta R1 prime R2 up to Rn is equal to what? Equal to the determinant of alpha C1 plus beta D1 R R2 up to Rn. Right? And so this is XM2. Because XM2 tells us when you apply replacement row operations, it will not change the determinant value of the matrix. So these two matrices has the same determinant value. All right, and this is the scalar multiply a row. So this becomes alpha C1 plus beta D1 determinant of R R2 up to Rn. But the idea will be the same for R1, R2 up to Rn, and this is C1 R replacement row operations. Okay, and here is minus C2. Go to here times minus Cn. Go to there to cancel them. So that determinant of R1, R2 up to Rn is equal to the determinant of C1 R, R2 up. Last one. All right, the last one, R1 from R2 C1R, R2 up to Rn by n minus 1 replacement row operations. So the determinant R2 Rn axiom number 3. So this is D1 determinant R, R2 up to Rn, axiom number 3. Okay, so up to this matrix by a scalar times a determinant of some particular matrix. The first row is R, the second row is R2, etc. And the same here, right? So the determinant of this matrix is a scalar times the determinant of the same matrix here. The same. They are the same. Similarly, same matrix here. Okay, to Rn, right? This is alpha C1 plus beta D1 of the determinants of R, R2 up to Rn. Okay, so from that result, we can split. This is as C1 determinant of R, R2, Rn. Okay, and this is alpha, and C1 determinant of the same this matrix. This is determinant of R1, R2, and we have done. Finish the proof. Any questions? So the idea is to find a media. The media is here. Okay, this is our common media. The three matrices. The three matrices appeared in the theorem. Okay, well, can be related to the determinants of some spatial type of matrix. But the possibility to find such a row vector R is because we have some preparation here, okay? With some preparation. Okay. Especially the theorem 4.1.d to give us the idea how to do the extension. Okay? So if the n-1 vector they are linearly independent. We make sure that it cannot span the whole n-dimensional Euclidean space. So there exists one that is very crucial for us. This particular, it can be, there are many choices, but you always can find one such a vector R outside of the span, such that when you append R into S, you enlarge the linearly independent state to have size n, and still remain linearly independent. And then again, apply the same theorem. We know this bigger theorem, this bigger set spans the whole n-dimensional Euclidean space. And so we are able to write down these two identities. Okay. Right. So that is crucial to have this identity. After some preparation, careful preparations, end up with these two identities. And then the rest of the part will be straightforward. Okay, just apply axiom number 3 again and again by using the operation. Okay, so let's take a 5 minutes break. So please come back at 11:25. Okay. Theorem 4.1.e tells us that the determinant function is linear on the first row. But actually, first row is not so particular, right? Actually, it's linear on any row. So for any I from 1 to n, and any n-dimensional row vectors, R1, R2, I minus 1, I prime, I plus 1, n, right, and the scalars alpha, beta, we have, so here is that the ith row may have, we have two ith row to combine to span the all to form linear combinations for the ith row. So the determinant of R1 I minus 1 alpha Ri plus beta I prime I plus 1 Rn. Okay, so this the determinant of this matrix is equal to alpha of the determinant of R1 I minus 1 I plus 1 Rn plus beta determinant R1 I minus 1 I prime I plus 1 Rn. So that it's linear on the ith row. Okay, and the proof now is the standard. Okay, so the determinant of this matrix R1 I minus 1 alpha I plus beta I prime I plus 1 n. Now you swap, you do your exchange of the first and the ith row. So you exchange them. When you do the exchange, you change the sign of the determinant. So the first row becomes to alpha Ri plus beta I prime. All right, and here is I minus 1 1 I plus 1 n. Okay, so by row exchange, this is theorem 4.1.1. Okay. Now you apply linearity on the first row, so that this is minus determinant minus alpha determinant of I minus 1 1 I plus 1 n minus beta determinant I prime I minus 1 1 I plus 1 n. Okay, so this is from theorem 4.1.e. And now again you swap the iso and the first row again. So when you swap them again, then you change the sign again. And so this is alpha plus beta I minus 1 I prime I plus 1 okay, and this down. So this is theorem. Okay, so we finish the proof. So the proof is standard. Okay, so I include a simple result as the last theorem of the first section is about elementary matrices. All right, so for any scalar alpha beta with beta not equal to 0, so we have a determinant of EIJ alpha is equal to 1. Determinant of XI beta is equal to beta. And the determinant of Pij is equal to minus 1. Okay. We just write down the determinant value for all the elementary matrices. This is true for any determinant function if it exists. Okay? It exists. So okay, so the proof is straightforward. Right? So the elementary matrix is the same as elementary matrix times identity matrix. So that so this says that you do the row replacement operation on the identity matrix, and by axiom number 2, you don't change the value, and so this is 1 by axiom number 1. Okay, straightforward. How about xi beta? So this is determinant of xi beta times the identity matrix, and so this is beta determinant of identity matrix by axiom number 3, and this is beta by axiom number 1. Okay. And finally, Pij. So this is determinant of Pij multiplied with identity matrix, and by theorem 4.1.1, when you apply no exchange on the identity matrix, you change the sign of that matrix, of the determinant of that matrix, and this is minus 1 by axiom 1. Okay. Okay. so that is all the results we have. So that is the basic, right? So we have a long introduction of the determinant function here, okay? Because the text will give you a very brief material on this subject. So I have put a lot of supplemental results for you. Okay. All right, so this section, I would like to study further properties of determinants. Right? But the main purpose of this section is to prove the existence and uniqueness of determinant function on n times n matrices. Okay. All right, so we first prove the uniqueness and existence of determinant function on 2 by 2 matrices. Remember, the example, the first example in the first section about a function defined on the set of all 2 by 2 matrices. Right? We have verified that it is a determinant function. So there exists the one. There exists the one determinant function, right? Already. So so consider, but we haven't verified the uniqueness of the determinant function on 2 by 2 matrices yet. Okay, so consider an arbitrary determinant function if it exists. EEC on M 2 by 2. Okay? So now since a row vector, a row vector AB can be represented as A 1 0 plus B 0 1. And so this is the row vector AB. AB can be written as, and the CD can be written as C10 plus D01. Okay? So by the linearity on any row, we have, okay? So the determinant for any determinant function on 2 by 2 matrices. Now, so this is the determinant of so you can think about that this is A. So it's A times 1 plus B times 0. Probably it's better to write it as AB CD. Right, it's better to look at the row vector, and so this is a determinant of A 1 0 plus B 0 1 CD. It's more convenient to look at the way here. And by the linearity for the first row, on the first row, you have A determinant of plus B determinant of 0 1 CD. All right, and next, CD can be represented as this linear combination. So that would be determinant of 1 0. So it's C 1 0 plus D 0 1. Plus B determinant 0 1 C 1 0 plus D 0 1. Okay. Now apply the linearity on the second row. So this is A of C determinant of 1 0 1 0 plus D determinant of 1 0 0 1. Right? Plus D C determinant of 0 1 1 0 plus D determinant of 0 1 0 1. Okay? So there are 4 terms. Now, the determinant of this matrix has 2 identical rows, 1 0 1 0. So the determinant value vanished. So this is equal to 0. Okay, the same as this one. 0 1 0 1. So the determinant is equal to 0. Okay, so we have only 2 terms here left. So this is AC, oh AD, sorry. So we have A and the T and determinant of 1 0 0 1. Okay. Plus BC determinant of 0 1 1 0. Okay. But this is just identity matrix. Okay. 1 0 0 1. But this one is not identity matrix, right? To turn this matrix to be identity matrix, you have to exchange these 2 rows. So once we exchange these 2 rows, you have this is 2 by 2. You might change the sign. Okay? You change the sign. So you exchange these 2 rows together. And so finally, the result is AD minus BC. So we start with an arbitrary determinant function. So if we have any determinant function on 2 by 2 matrices, then the value of this determinant function must be AD minus BC. So the value is unique. Okay? No other possibilities, because we just follow our properties up to now. Okay? So that we have this one. So we apply the linearity already. Okay? We get that? Any questions? So we conclude that determinant of ABCD is equal to AD minus BC. And this is just the D function in example 4.1.1. Okay? Because we define a D function in the first example of the last section to be AD minus BC. And we have shown that this function is a determinant function already. And here, what we have shown is that if we have other determinant function, this function must be the same as this. So this shows that there is one and only one determinant function on 2 by 2 matrices. Okay, so we have one step further already, right? Well, because we already showed the existence and uniqueness of 2 by 2 of determinant function on 2 by 2 matrices. But still, a little bit distant from our goal, because we want to prove this fact for any n by n matrices. All right, so here we want to develop further properties of determinant functions. Okay. Right, the first one is a supplemental lemma, 4.2.8. Okay, and actually, I find that it's a statement in an exercise. I mean, probably the last exercise. For any 2 by 2 matrices, A and B, n by n, sorry, for 2 n by n matrices, and the product of A and B is invertible if and only for both A and B are invertible. Okay. And the proof, I think you know that, but let me just do it briefly. Since AV is invertible, okay, there exists an n times n matrix called C, such that AB C is identity. Okay. So this implies that A, B, C by associativity of matrix multiplication is I. All right. So that A is invertible because B, the product B and C, this product is a right inverse of A. If a square matrix has a right inverse, then it is invertible from the invertible matrix theorem. So the A is invertible, right, by the inverse matrix theorem. And similarly, C, right? C is a left inverse of AB, right? Because C is the inverse, so this is identity that implies CA, and the B is identity. All right, so that B has a left inverse, which is C times A, multiplied with A. So that B is also invertible. For the same reason. Okay. So the forward part is good, but the backward part has been proved already in chapter 1, 1.2.d. Okay. We need this the backward part at that time, so we prove that. Yeah. Anyway, so this is simple lemma. Okay, now I present a lemma in the textbook. So for any n times n matrix A and alpha, beta and the scalars alpha, beta with beta not equal to 0, we have the determinant of EIJ alpha. Okay. Now, the product of these two matrices, right? Here, this is an elementary matrix corresponding to a replacement row operation. But so we know, we want to show that this is, we have a so-called product manager. So this is actually, so the determinant of the product of these two matrices is equal to the product of the respective determinant. Okay. Similarly, for xi beta, we have and determinant So actually this lemma is a special cases of product formula for the determinant function. I think this proof works. It's quite simple. So determinant. This is just equal to determinant of A by axiom number 2, right? Which by axiom number 2, and so this is 1 times determinant of A, but 1 is the determinant of EIJ alpha, And this is from theorem 4.1.2. Okay. The last one. Okay. The result here. Right. Now how about the scaling? Okay, so this is the beta determinant of A by axiom number 3. Okay, to get this one. But the beta is the determinant of xi beta, the determinant of A. Again, this is by theorem 4.1.3. The last one, determinant Pij A. This is minus determinant of A. So this is from theorem 4.1.1. Okay. And this is minus 1 times the determinant of A. But minus 1 is the determinant value of Pij. Again, this is the theorem 4.1.2. So we have done. Okay, so there are special cases of product formula. Now with this lemma, now we are able to prove the general product formula for determinant function. So that would be theorem 4.2.2. We call it product formula. Okay, so for any two n by n matrices A and B, we have the determinant of their product is equal to the product of their determinants. Okay, so you compare with this lemma, you can see this lemma is just a special case of theorem here. But the proof of the general case need the special cases. All right, so the proof here. So it's okay now? All right, good. Right, and therefore, so we apply the sequence of elementary matrices to A, and we end up with an identity matrix. And also, when we apply the same sequence to the product A times B, all right? So if we do this one, we find that this is EK, EK minus 1, E1, A, and B. And this is B. Okay, so now, 1 is the determinant of the identity, and this is the determinant of EK, EK minus 1, E1, and A. Okay, and now it's EK multiplied with this matrix. So applying lemma 4.2.1, this is the determinant of EK and determinant of EK minus 1. That's E1A. And you can continue to apply. So this is lemma 4.2.1. So when you continue to apply lemma 4.2.1, you can factor out okay, so you have that. Okay, so you apply lemma 4.2.1 repeatedly. Okay. So 1 is equal to determinant of EK times determinant of EK minus 1 times etc. Determinant of E1 times determinant of A. And similarly, determinant of B, okay, it comes to determinant of EK, EK minus 1, E1, AB, okay. So again, you have determinant of EK, determinant of EK minus 1, that's E1, AB. So finally, you have determinant of EK, determinant of EK minus 1, determinant of E1, and determinant of AB. Okay, and so this is here, here, and here. All apply lemma 4.2.1. Okay, and so suppose this is one formula, two formula, so that you take, say, 2 divided by 1. Okay, this implies that 1 divided by determinant of B no. 1 determinant of B divided by 1 is equal to a lot of things. Determinant of EK, determinant of EK minus 1, determinant of E1, determinant of AB, and the numerator is the determinant of EK, determinant of EK minus 1, the determinant of E1, and determinant of A. Now, everything here, all the factors in the denominator is non-zero. Why? Because the determinant A is non-zero, because A is invertible. So we are sure that this is okay to put into the denominator. How about all the other factors? Well, from this theorem, all the determinants of these elementary matrices is non-zero, right? 1 over beta, beta not 0, 1, minus 1. So it's okay, right, to put here. So we can cancel them. And and move the denominator to there. So we have determinant of AB is equal to determinant of A and determinant of B. And we have done. Okay, so we finish the product formula here. Any questions? Okay, so even though the special cases are simple, the lemma, but the general case is indeed a kind of repeatedly applying the special cases here to there. Okay. So, so once again, elementary operations so powerful, right? Even though they are very simple, but they are really powerful. That to facilitate us to prove theorem, actually like this one, the product formula. It's not trivial, actually. Okay. Okay, so I stop here, and remember, next Wednesday we will have first midterm examination. Start at 10 o'clock, not 10:10. Okay, 10 o'clock. So, and the coverage will be from chapter 1 to chapter 3. And I will now assign exercise this week. I want you to spend your time for the preparation of the midterm examination. Okay, but we do have TA office hour the same time Monday, next Monday, from 6:30 to 8:30 in this classroom. So you are welcome to come here to ask questions, and TA will be here to answer your questions. All right. Okay. So see you next week.